My name is Elena Sutley. I'm an assistant professor in structural engineering at the University of Kansas. 127 million people live in coastal counties in the United States, and at least 10 million of those people live in counties or live in areas that are susceptible to regular flooding. Living in elevated structures, right? That's a really common building type to help prevent your home from being flooded or from experiencing damages from storm surge events. But those structure types in these areas that are susceptible to storm surge and flooding are also susceptible to high winds. And when we elevate buildings, we're changing the aerodynamics of that structure. My colleague and I, Tom Dow at the University of Alabama, were really just getting started on our research on this topic of elevated buildings. When we learned and had talked with Dr. Chowdhury to learn that they had just completed wind tunnel testing at Florida International University on really similar building types. And so when we were able to get our project funded, we were able to then bring his data in to strengthen, I think, both parts into a much stronger body of work. So what's so great about this research is that we're studying what that wind component is, and we're able to move it into the code or into the standard so that we can start designing buildings intentionally for those wind loads. And so I think our overall expected significance of this project is that we'll have better, safer, more accurate wind design of buildings that literally millions of Americans are already living in high wind regions. So far, we do have some outcomes. We've been able to publish 2 papers. Hopefully, our findings from this collaborative research between our fieldwork and the FIU wind tunnel test data will be able to be adopted into practice into this standard by 2022 and be in use.
Hello, I'm Nigel K. I'm a professor of civil engineering at Clemson University, and I've been working with the Wall of Wind on a project to look at the removal of roof gravel from rooftops during severe storms. And then after that, we're going to go back into the Wall of Wind and we're going to do some destructive testing. And we're going to use that destructive testing where we actually remove gravel at full speed, at full scale and high wind speed to see whether or not our predictions hold up. So hopefully once we understand all the conditions under which roof gravel can be removed during severe storms, we can develop mitigation techniques so that people can go back to existing buildings and maybe make some adjustments to parapets or other things to prevent roof gravel blowing off in severe storms. And then also designers of new buildings would have guidelines so that they can understand how to avoid that damage.
Hi everyone, I am Abdullah S. I'm a faculty member in the Department of Civil, Environmental and Geodetic Engineering at The Ohio State University. And I have been fortunate to be involved with Wall of Wind experimental facility in a NSF project looking at the hurricane impacts on transmission systems. And the objective of the project is to see how vulnerable the power grid, especially in the transmission system, is against hurricanes in particular. We want to find what is the likelihood of failure of the units, basically towers and conductors, and system of units against different intensities of hurricanes. And from there, we can then characterize resilience and inform the design process to improve the resiliency of these systems. And the results have been published in several national and international conferences and presented in those avenues, and also multiple journal papers. There are several journal papers that are also on the way. We have produced results that are going to improve the way we design, analyze these structures, and we are envisioning submitting these findings to code committees in ASCE to revise the code and improve the design process. So we are able, with these models that we are developing this project, to target the towers that need to be upgraded and how we can optimally upgrade them in such a way that the resilience is improved with a minimal cost.
My name is Alice Alipur, and I'm an associate professor in the Department of Civil Construction and Environmental Engineering at Iowa State University. In this NSF project, we will use the NHERI wall of wind experimental facility at Florida International University to assess and characterize the loading on transmission towers and transmission systems. So aeroelastic models of transmission towers and also conductors and a multi-span system will be used to test these systems under the high wind velocities that can be generated at wall of wind facilities. And these loading will be used to validate the high fidelity finite element models that are developed through this project. The system reliability assessment component of this project will help with understanding the impacts or the extent of power outages that would happen under different scenarios of extreme events in the communities. And as such, the decision makers and community leaders can plan for the rapid recovery and restoration of damages after extreme events occur.
Hi, I'm Katherine G. I'm an assistant professor in civil and environmental engineering at Stanford University. We've worked with the wall of wind in the past on modeling the pressure coefficients on a high-rise building, where we've looked at validating mean, root mean square, and peak pressure coefficients, both against the previous wind tunnel experiment and against computational fluid dynamics simulations. Right now we're working on a similar project, but there we will look at loading on a low-rise building, both just a single building and a building in its complex urban environment. The goal of our work is really to validate our computational fluid dynamics simulations so that we can actually show that these can provide accurate predictions on wind loads on buildings in urban environments. And ultimately the goal is to have CFD become an accepted tool for design so that it's incorporated into building design codes as well.
My name is Chris Letchford. I'm the head of civil and environmental engineering at Rensselaer Polytechnic in upstate New York. I've been involved in a project at FIU Wall of Wind, in particular to examine the scale effects on separation bubbles at very high Reynolds number. And we were able to take some very interesting results on pressure and velocity fields on our model at FIU. And the hope is ultimately to make sure that when we do wind tunnel studies at very small scales of tall buildings, that what translates from the model to the full scale is accurate. And this is able to be achieved at FIU because we can run at very high speeds in very large models. So the importance of this work is really to validate wind tunnel testing of all buildings, in particular tall buildings, which are often conducted at very small scales, 1 to 400 or thereabouts. And this leads to Reynolds number disparity, 2 or 3 or even 4 orders of magnitude below the full scale. And so by doing this work at FIU, we trying to make sure that what we measure in a wind tunnel on a tall building, pressures on windows and cladding, is in fact reflected at full scale. And we can achieve this at FIU because of the large scale model that we're able to construct and the very high wind speeds that are able to be done. The work at FIU, we proceeded with a lot of flow conditioning work. So getting the flow in the facility to our level of standard, very high quality, low turbulent flow. And we spent a lot of time documenting and improving the flow. And it was excellent work by the staff at FIU in helping us achieve that flow condition.